So in this video, we'll be going over two problems that I think are pretty good tests of your understanding of how to generate a MacLaurin series using the Taylor series coefficient sequence. So we'll go over this first one, which will just ask us to find the first 5 terms. It won't ask us to actually, produce the representation of the given series, but I'll still do it just for good measure. And then the second one will ask us to find the MacLaurin series representation of f by any method. And then we would want to, of course, also simplify that so that there's nothing left to the sigma notation to fully clean everything up and show we have good understanding of what's going on. All right. So first thing you always want to do when generating your own Taylor series or MacLaurin series is, ask what's actually being asked of you. So recall that the coefficient sequence formula is just going to be the nth derivative evaluated at 0 over n factorial times x minus a over n, right? And we know that a MacLaurin series has a center of 0. So x minus 0 is just going to be x to the n, right? That's going to be what we actually are going to end up using. So all we have to do is now just, start getting each part. So we'll start by getting the nth derivatives. And of course, we want 5 terms. We know the first term is going to be 1 here, just because that's usually what the first terms are going to evaluate to. So now we just have to differentiate our original function, which was, I believe, 1 plus x over 1 minus x, right? And so now we are going to differentiate it as many times as needed to get 5 terms, right? So we have 1 term already, so we really only have to differentiate it 4 times, and then we should be good, right? So looking at this, we can see that we're going to have to use quotient rule, and it's going to be kind of messy, right? Because if you look at this, it's going to be x times 1 minus x minus negative 1 times, oh my bad, this should actually be just a 1, negative 1 times 1 plus x, and then we're going to get all of that over 1 minus x squared, and then we're going to have to clean that up, and we're going to have to do that every time, which is, not impossible, but it's more work than we probably would want to have to do, especially on a test. That can get kind of long and tedious. So let's kind of approach this more intelligently, right? So we know that with, rational functions like this, we can kind of decompose them into more simpler forms to work with. So we can do it, a variety of ways, but a quick way that you can do kind of a mental shortcut one is kind of look at this and, see here, look at the bottom here and see how we can get this to as close of the top as possible, right? So obviously the biggest difference here is that they have flip signs. It's 1 plus x versus 1 minus x. So what if we just, multiply this bottom by a negative 1, right? And we'll try that for our numerator and see what happens, right? So we'll do negative 1 times 1 minus x over 1 minus x, right? And so now, if we were to actually expand this out, we would see that it would go out to negative 1 plus x, right? And so that's pretty close to 1 plus x, isn't it? It's just off by what? It's off by this difference between negative 1 and 1. And we know that 1 minus negative 1 is 2, right? So how do we fix this? How do we make this equivalent? We just add 2. And we know that we have to keep the same denominator. So do plus 2, 1 minus x. And then we check to make sure that this is proper identity. So let's just do negative 1 plus x plus 2 over 1 minus x, and that should simplify to this. So let's check. Negative 1 plus 2 is 1. X is not being multiplied by anything, so it's added to anything except 0, so it's plus x over 1 minus x, which is an identity that matches that original thing we started with, right? So now we can instead, oh my bad, we should actually use the original value we had, so negative 1 times 1 minus x, and we should note that we can cancel that right off the bat, so that's negative 1 plus 2 over 1 minus x. And so these are the kind of manipulations you want to do to save you some time, right? Because now looking at this, isn't this much simpler to differentiate, especially multiple times, right? Because we know that this, after the first differentiation, is going to be 0, and then this 2 times 2 over 1 minus x, can't we represent even that more compactly, right? We know that any irrational function, the bottom, or rather the denominator, if it's raised to a power, can be expressed in terms of a negative power, right? So by that I mean, if we had a over x and x is raised to n, we can instead represent this as a x to the negative n, can't we? And so using that property, we instead represent this as 2 times 1 to the negative 1, or 2 times 1 minus x to the negative 1. And then differentiating this is, of course, much simpler, much faster than, having to do chain rule and all that. So we know that we simply use power rule. So we bring the negative 1 down, multiply it, so we get negative 2, and then we differentiate the inside, but we leave it alone at first. We multiply by the differentiation of the inside using chain rule, so that would cancel, and this would be negative 1, so we multiply by that. So we know that the first derivative then is just going to be, again, 0 plus 2 times 1 minus x to the negative 2, isn't it? So that would be, our second term. So now let's differentiate it again. So taking this, 1 minus x, negative 2, again, just use power rule. And then we know that the inside, of course, is going to be a negative. So we know that outside should stay positive since we're going to be multiplying by 2 negatives. So just 4 times 1 minus x to the negative 3. And so kind of seeing the pattern here, should already be kind of apparent what's going to be happening. We're just multiplying by the, power rule. And then this is going to keep the same sign. So it's just going to be 12, 1 minus x to the negative 4. And then the fourth derivative should just be 48, 1 minus x to the negative 5. And that should be, 5 terms, as we said, 1, 2, 3, 4, in addition to that 1. So this part is done. Now we can move on to this part. And all we're doing here, again, is just plugging in 0 to these derivatives that we've built. So evaluate this for 0, 2 times 1 minus 0 to the negative 2. That's going to be 2 times 1 to the negative 2, and anything raised to 1 is just going to still remain 1. So we know that the first coefficient here is going to be 2. Same thing here, 4 times 1 minus 0 raised to the negative 3, which is 4 times 1 to the negative 3, which again, same thing. So we can kind of see the pattern here. This is basically just going to be 12, and this is going to be 48, right? And so those are the coefficients that we have on top here. And so now we want to multiply that by x to the n. So we take all these terms here. 1 plus, we have what are 2 x to the n plus, what's it, 4 x to the n plus 12 x to the n plus 48 x to the n, right? And are we done? Nope, we're not, because, we still have to do our factorial here. So now let's just go ahead and add that. 1 over 0 factorial over 1 factorial over 2 factorial over 3 factorial over 4 factorial, right? And then we want to go ahead and actually put in the appropriate values. So for this, sorry, that messed up there. 1, 2, 3, 4. Right? And then can we simplify it any further? Yep, we sure can. So this one is just going to be 1 plus 2x, then 1 plus 4 times 2, or 4 divided by 2 should just be a 2, x squared, plus 3 factorial is going to be 6, so 12 divided by 6 should be 2x to the third, and you should kind of see the pattern here. 4 factorial is going to be 24, 48 divided by 24 is going to be 2. So we see that these coefficients are all just going to be 2, right? 2x to the 4, 1, 2, 3, 4, 5, right? And so these are our first 5 terms of the MacLaurin series for the given function 1 plus x over 1 minus x. So we would technically be done there. We've done all the work necessary to prove it. But if we wanted to go a step further and say, actually, show what the power series representation would be, well, let's just do a little analysis here, taking a look at things, right? So going back to the original function, right, we had 1 plus x over 1 minus x. And so looking at this now, you can see, kind of take a look here. We know that the coefficient, right, if we use the form 1 over 1 minus x is equal, because this is the power series representation for a geometric series, x to the n, right? And we know that that usually is ax raised to the n. So looking here, right, what's our coefficient? 1 plus x. So it would just be, and we know that the bottom fits it perfectly. We don't have to do anything here, just 1 minus x. So this x to the n is just left alone. It would essentially just be n equals 0 to infinity, 1 plus x, x to the n, right? And so if we wanted to double check that, this should be correct, but let's go ahead and, do some terms just to make sure. So the first two terms, we can just use if we're starting at 0. Well, let's just do 1 plus x times x to the 0, right? Anything goes to the 0 power, it's just going to be 1. So the first term is going to be 1 plus x. So then we go 1 plus x, x to the 1, and then we do 1 plus x, x to the 2, plus 1 plus x, x to the cubed, plus 1 plus x, x to the 4th, right? And so looking at this doesn't really seem to match up to what we have, but we know everything is correct. So let's just try maybe, simplifying things. Maybe we'll get, something close to this. And so let's go kind of with that approach, right? So are there any other, well, actually, let's just simplify everything first. So 1 plus x plus 1 plus, or x to the first. So x plus x squared plus x squared plus x cubed plus x cubed plus x to the 4th plus x to the 4th plus x to the 5th, right? And so we do see that there are actually quite a few repeating terms here. It seems like every kind of, almost like a telescoping series, right? We're kind of seeing that the middle terms are summing together. So we'll actually see here that we have 1 plus 2x plus 2x squared plus 2x cubed plus 2x4 plus x to the 5th. But we know that if we were to do the next term, right, we would get a 2x to the 5th and then plus an x to the 5th. And then after that, it would continue on in that same pattern, right? And so now looking at that, doesn't these first, few terms here, 1, 2, 3, 4, 5, seem to match up with our first 5 terms here? And so then knowing that, we know that this actually is right here correct power series representation of this given function. So moving on to the second problem, we have find the MacLaurin series representation of the function by any method. We must leave nothing to the left of the sigma notation, however, though. So let's look at the function. We have x cubed times sine of 2x squared. And so looking at it, kind of the first thing I want to do is just isolate what we know is going to be the function that's actually going to be represented by power series, right? Which we kind of suspect here. Or rather you should suspect is going to be, this part, because it has a striking resemblance to the sine x series. So we'll go ahead and isolate that to make the analysis a little simpler. 2x squared, right? And so now we only have to worry about this because we know that this is the same as if we had whatever power series we need to use, right, multiplied together. So we can do that to make things simpler. And again, we know that this is going to be using the same power series form as sine of x, which recall, should know, and I don't really recommend memorizing them so much as understanding kind of what the sine series does, right? And then from that, you can kind of rebuild the series pretty easily in your mind, right? We know that sine is going to alternate, which we know alternating can be best represented by this. And we know that only the odd terms of the sine function are going to be preserved. And so how can we best represent, oddity, right? We know that that would be 2n plus 1, because even is just going to be 2n, right? Because if you think about it like this, what's n equals 0 here? It's going to be 0. And then if n equals 1, then it's 2 times 1, which is 2. What's n equal to 2 would be 2 times 2, which is 4. And then n equals 3 is 6. So you see that only the evens are preserved when we use 2n, right? And then 2n plus 1, obviously only the odd terms are going to be preserved, right? 2 times 0 is going to be 1. If n equals 1, then it's 2 times 2 is 4. Or rather, sorry, 2 times 1 is 2, plus 1 is 3. N equals 2 is 2 times 2 is 4, plus 1 equals 5, and so on, right? 7, 9, 11, right? And so that's how you can kind of, recall the general forms. So we know the bottom, of course, similarly is only going to be the odd forms as well. And so now we have rederived the sine x series, right? Now what is next, right? Well, we know this is for sine of x, so what about sine of 2x squared? Well, all we have to do, of course, is just substitute this into here. So wherever we're seeing x, we're just putting 2x squared. So nice and easy then. That'll just be that. Obviously, this is not getting touched. Again, we're only replacing where we see an x. which is really only one place. So 2x squared raised to the 2n plus 1 power to represent oddity. And of course, the factorial on the bottom is untouched as well, right? And so remember, of course, this is all still being multiplied by x cubed. And so is there any way we can simplify this further? You should note that really the only thing we can simplify is this here. So let's go ahead and do so. We see that we are going to be using the exponent rules for, of course, multiplying the exponent factors, right? So you can imagine this as 2 times 2n plus 1. So that should be 4n plus 2, right? If it was, 2x squared times 2 to the 2n plus 1, then you would add them. But because we have the 2n plus 1 raising the basis function there, then we have to actually do multiplication, right? And so that should leave this term instead being 2. Sorry. We should also remember, of course, we're going to be raising these individually, right? The coefficient is going to be raised individually of the x squared. So it's going to be raised to 2n plus 1. And then we have x to the 4n plus 2, right? So we have the x squared and we have the 2 to the 1. So that's what those are going to be changed to. And so now we have to bring in the x cubed, right? Because we don't want anything to the left. Well, we know that by commutative property, of course, we know that we only really need to worry about, simplifying this in regards to the existing basis function of x. So we're just going to multiply x cubed times x, basically. That's all we really need to do. Let's rewrite this. And it equals 0 to infinity. We know that this is going to be untouched. We know that this is going to be untouched. So we know that really all we're doing is x cubed times x to the 4n plus 2, right? And then of course the factorial is untouched as well. So this is all we're concerned with, right? This is all we have to look at. So we know that we are multiplying them, and we actually just kind of mentioned that when we're multiplying, we just use the addition or the summing of the exponents instead. So it's 3 plus 4n plus 2. Well, we can only add like terms. So the 4n is left alone, and we just get 4n plus 5. So go ahead and replace this with just an x to the 4n plus 5, and that is it. We are done. We have very compactly represented the power series, or rather the MacLaurin series representation of this function x cubed sine of 2x squared, and it is thus, right, fully simplified. And that's all we have to do. Obviously, if you wanted to, you could, write out the first n terms here, just, wherever you see an n, plug in a 0, then plug in a 1, 2, 3, 4, and so on, right? And then I'll give you a nice approximation up to, n factors of the, or rather up to n terms of the MacLaurin series representation, right? But we will go over doing that in a different video. For now, this is all we need to cover, and I hope that this has helped, and might do a few more, going over some more test-like problems regarding these, but again, that's all for now. Thanks for watching.